Okay, so thanks for joining me today, everybody. Looks like we got uh, over 30 attendees, so that's great. Going to do some basics today with SurvNet, and just to give you guys a little bit of background on me, I'm a licensed surveyor in Michigan. Got licensed back in 2000. I started working for Carlson a couple of years ago, so the whole software thing is a bit new to me. So it's not like I was born and raised in the software environment here. I was a practicing surveyor for a long time, and I did use SurvNet for quite a few years in private practice. So I've been in your shoes. I've done the digging, I've done the sweating, I've done the freezing, all that good stuff. And now I do a lot of SurvNet support. Um, Private practice for about 15 years. I had my own small company. I did mostly boundary work. And I really struggled early on as I worked in the same county day in, day out, putting together jobs that started creeping into one another, and really needed to find a better way to manage my data, get everything on the same system, implementing state plane coordinates, and really having all the jobs tied together in one system. And at first I struggled. I was translating and rotating, trying to get my coordinate systems to line up. And then I got into GPS, and I thought to myself, there's no way that I shouldn't be doing everything on state plane coordinates. I really want to go that route. I think it'll really help my business. So that's what I did, and I found SurvNet, and really didn't know anything about least squares. This is over 20 years ago. Other than maybe a class or two in college, which gives you some basics in it, and that's about it. So I, thought, well, I'm going to give it a try, and I did get a lot of help early on from some of the early programmers of SurvNet with Carlson. They were very gracious with me and gave me a lot of good support and got me started. And that's really all I needed. I was not, I'm not a mathematician. I'm not a programmer. I'm just a regular surveyor, just like you guys. I mean, I spent more time staring at deeds and trying to figure out title messes and location messes than anything else. But I did use SurvNet very much to my advantage, fell in love with it, really changed the way I did things. So I really enjoy sharing that knowledge with other surveyors that still have boots on the ground. So today, the setup that I've got that I wanted to work over it's a really small survey, but what it does, I'm going to zoom in. I know you guys can see my screen. It's going to combine some GPS work with some total station work. And in this case, this is a data set that was put together by Lad Nelson over in Wisconsin, Iowa area. And he ended up bringing in some state plane control with a couple of from a couple of different core stations, one in Iowa. You can see the Iowa core is base point 609, and to the east we got the Wisconsin core is base point 61. So what happened here was with a network rover and an N-trip connection, a couple of points were set on the job site, and then those points were utilized to traverse from. So it's a really good way to get state plane onto a job, get those good state plane coordinates, and have some relative precision with the precise total station work. So if we zoom into this, we'll see what we've got. We've got the red lines are our GPS, and we basically got 2 points 11 and 12, where the vectors are coming in from the cores. So each one of those control points, point 11 and point 12, have a vector to each one of the cores. So those points were brought in that way, and then we did a three-dimensional traverse to tie it all together. So one of the things in SurvNet is if you are doing GPS work, you have to be working in a 3D model. And so if you do combine your traverse work with it, you do have to carry your rod heights and your instrument heights. That's not always necessary. If you're just doing horizontal work, you can get away with doing a couple of different things to get by. But the first thing we should do before we get into this really deep is just go through the settings. Once you have a basic understanding of the settings, we are in really good shape to move forward with the data. So what I'm going to do is I'm going to go to the survey menu. I'm going to go to SurvNet least squares, get this opened up. And now I'm in 2023 right now. This is the docking dialog. In 2020, we came out with this docking dialog. Prior to that, it's the standalone dialog. So if anybody's got an older version, it's going to look different. It's going to be totally standalone. You don't have the CAD graphics. You have a separate graphics engine. The CAD graphics now are much, much better because we're using IntelliCAD or AutoCAD, depending on what you're using for an engine. But this is, it's all really the same stuff. All the settings are pretty much the same. It'll look really familiar depending, if you're in the older system, that's fine. If you're in the newer system and you like the older system, there is a way to use that older standalone dialog. But let's go through the settings right off the bat. And in the SurvNet menu system here, if we go to the gear, that's going to bring up all these settings. We've got multiple tabs. And I like to work through them from left to right. And once we have a basic understanding of all these settings, then we can start bringing in our raw files and get into processing the data. So the first thing we need to do is when we're in SurvNet, when we're using GPS, we've got to be in a geodetic coordinate system. So we're going to go to a grid system, and through that we can define our projection and find wherever we're working. In this case, we are working in the Iowa zone 11. We've got our units. Scale factor, we typically leave that to 1. And for our coordinate system, since we are GPS, we do need to use the 3D model. If we're doing traversing only, and we're outside of GPS, we can use a 2D model. But for this, we're going to use a 3D. And we're also going to apply the geoid. So that is all pretty much straightforward stuff. We want to get that all set up before we get moving. And the next tab we'll get into is the input file. A couple things on this that are pretty important. One of the things that I use in this job, which is really handy for most of you that are in practice, when you're tying into the cores, if you've got a network rover and you're bringing control in through the cores, one of the things we can do for control, instead of looking up a published coordinate for that control point and bringing it into the raw data or into a supplemental control file to be read, is we can just tell it, use the BP records, use the base point records as control. So in the raw file, it sees the base point records for the Iowa station and the Wisconsin station, and it's going to hold those positions for us. So for this job, I'm not adding control points per se. I'm just telling it to use the base control points, the base points as control. So it's a really quick way to bring control in without adding like a text file that has state plane coordinates for those positions. Other than that, in this situation, we've got total station, what are our units? We've got those set to US feet. We've also got one for include any GPS vectors. This is a little bit confusing. I've got that turned off in this case because all of my GPS vectors are stored in this, off to the left, you'll see where it says GPS files. This setting right here is if you have GPS vectors in this case, in the raw file, in this case, the SurvNet revised etl.rw5. If you have vectors in that file, you turn it on there. But if you've got your vector files underneath the GPS files, then you don't have to worry about that setting. A lot of people will change this to feet because they're working in feet. We want to keep that in meters because our vectors are always coming in X, Y, Z in meters. Another thing that you can do in SurvNet, we're not going to go over it today. We can include differential leveling. We can add that in as well, which is really, really awesome. We don't have that today, so we're going to leave that alone. And supplemental control file, what type of file format are we using? This kind of gets into the use base point records as control discussion I just had, where if you had a text file or a CRD file that you wanted to use that have control points in it, you can say, I want to use, maybe I've got a comma delimited file that I want to use, you can set it to that, and you would actually import that over on the left into the control files. But we're not going to use that in this case, so it's not going to be in play. So that's just what it says. It's input files. We'll get over into pre-processing, and there's some pretty important stuff in here. Apply curvature and refraction. That is for when we generate the coordinates. Do we want to apply that? You might want to check your instruments on that to see if it's applying for that in real time, like the curvature and or the refraction. I think different instruments handle those things differently. Point number substitution string. This is really a key issue here. When you're doing your field work, we're doing least squares, so we've got redundancy. That's the whole point. A lot of people will keep the true point number through the whole job. So let's say you're traversing, you measure to 0.5. Later on, you tie into 0.5 again. You see it from another traverse point, whatever. A lot of people don't want to call it 0.5 in the field. They want to call it something different. They want to, keep those separate when they're in the field. So let's say coming back around, instead of calling it 0.5 and overwriting it, I want to just call it 0.105, something like that. I can do that, and in the description where I enter the description for the point, all I have to do is say equals 5, and because we've got this setting set to equal, it will treat that 0.105 as 0.5. So that's something really handy that a lot of people like to use if they like to keep their point numbers separate when they do, start tying into the point multiple times. And we'll get into that. We'll take a look at the raw files and go through them a little bit so that we see all the information there before we do the adjustment. Compute closures. This is really a neat tool. What we can do is actually set up, and I've got one set up here, where we do have a closed loop, and we can actually look at the standard closure ratio if we want to, and also the angle balance. And that is something that, for two reasons we have that, really. I mean, some people still want to know. They just want to know their closure, and that's fine. It's great for that. Sometimes we have reporting, maybe statutory, where the closure has to be shown still, so we've got it for that purpose. It's also nice if you've got multiple loops in a job where you've got the potential for multiple closures, and you've got a bust, something's falling apart in the network, you don't know where it is. You can run those closures and actually see, well, 2 of these 3 close, a third one doesn't. Somewhere in that area, I've got a problem. So it serves a purpose. It has no implication whatsoever on the adjustment itself. The adjustment's going to be least squares. It's not doing a compass rule adjustment or anything like that. It's just looking at that raw data and computing a closure and reporting that value to you so that you can use it to report on your survey or to try to isolate a blunder. So we do have a point list set up, and these are my traverse points where there's a closed loop. So I've got that set up and ready to go. We've got some tolerances where if we want, and you'll see when we run the adjustment, that if there's a tolerance that is exceeded in the raw data, like if you measure slope distance to a couple of points more than once, and this tolerance of 200ths is exceeded, it's going to flag that and just put it in the list. It's really nice. It's at the beginning of the report. If there's something really crazy where you've got a big discrepancy between 2 measurements, it's going to pop right out at you. But I don't want to see every single one of them, so I try to set these to reasonable values, a couple of hundredths, maybe even more than that, and just report really big outliers. And you can always adjust these if you want. After you do an adjustment, you want to say, I want to change my pre-processing so that it helps you isolate where you might have some problems. So we can do that for the horizontal angle, the distances, and the vertical angle. We also have the angle set spread display. I typically keep this at, actually I've got this at show individual angles. I like it to be at the sets. So it's not gonna, your tolerances for your angles aren't going to be individual angles. It's gonna look at a direct and reverse set as one angle. And when it sees a discrepancy between the sets, that's where it's going to flag it in the pre-processing. So little stuff, but good to know. And there's probably going to be some questions. We can probably grab those, I believe, then at the end of the session. So if you do have them, we'll try to get to those later. Standard errors. This is a huge thing for us that we really need to understand. These are standard errors. We're telling the program really what we can expect out of our equipment. And so when it does the adjustment and comes up with residuals, it compares the actual residual values to what's expected based on the standard errors that we place in here. So we want to keep these really reasonable. This is where people sometimes cheat the system to try to make their chi-square test look better by inflating some of the standard errors. We always want to keep them reasonable because that doesn't serve any purpose to inflate them. So for distances, we have a constant value. You can pull this right out of your gun specs. I've got 100th plus 5 parts per million. And we've got angular, horizontal, and vertical. We've got a pointing and a reading, where the pointing is the human factor, and the reading is more of a least count situation. So general rule of thumb, 5 seconds a piece is reasonable, but you can customize those, change them around. And these standard errors are global, so it's going to cover all of the raw data. I should point out that one thing that's really powerful with SurvNet is in your raw file, it's going to be using all these globally. But let's say you've got a situation where you had a really hard time, for example, with heat waves. Even if you got robotics, they still struggle. Really bad situation where you just had a hard time getting your angle sets to close tightly. You can actually add individual standard errors inside the raw file that overwrite a portion of the raw file. So let's say that we've got one angle set was really tough. We can get into the raw file and add a standard error setting there just for that one angle setting. And then after that one angle, we can actually tell it to go back to the project defaults, which is this tab that we're looking at right here. So these are global, but you can customize the raw files to really, make it more intelligent. Another example would be, let's say you've got a closed traverse, you're going tripod to tripod, you're force centering, and then one of these points that you shoot a side shot off of it, and you shoot it, with a tripod and tri-brac, really good centering, everything's really tight. And then you see it from another one of your control points, but you've got a hill there, you've got a really high rod, it's up 10, 12 feet in the air. We might want to change for that one shot alone, we might want to change our centering error for that shot so that it's not at 5,000ths of a foot. So really, really nice to be able to customize those. But these are global, we want to get them all reasonable. I've got my target centering to 5,000ths, instrument setting to 5,000ths, my heights, 100th on both of those for target and instrument. You can also put in an azimuth for control. We don't have one of those in this case, but you can set the standard error for your azimuth. You can also do that for your control. And if you guys remember, in this case, our control is the cores. And they're many, many miles away. We can weight them by putting in a value like 500ths, that type of thing, 500ths and 1,000, maybe a 10th for vertical. But in this case, I'm just going to leave them fixed. I'm going to keep them at 0. They are cores and they are quite distant. We've got some differential leveling standard errors. We've also got GPS standard errors. GPS is pretty straightforward. We've got centering, which is if you're using base rover, it's your base and it's your rover. And this is in meters. I've got it set to 3 millimeters, so we're at about 100th on the centering for that. And the vector standard error, I've got that set to 2 in this case. I just seem to work with this. I actually don't go higher than 2 at all, typically, but that is basically it's a scalar. It's exponential, essentially, where we've got vectors that have built-in precision values. A vector consists of delta x, delta y, delta z, variance, and covariance. And it's the variance and covariance that SurvNet reads to tell how good that vector is, so it knows how to weight it in the adjustment. So it's not going to For example, if you measure from point A to B multiple times with GPS, you get 3 different answers. It's not going to take a mathematical mean of those. It's actually going to look at the quality of the vectors. And the quality of the vectors are notorious in GPS for being overly optimistic. So oftentimes we scale those. I've got that set to 2, which is 2 to the factor of 2. So it's actually scaling them by a factor of 4. And I don't like to exceed it. I did use it on this. If we have time, we'll go through some adjustments and change standard error settings, and you'll see how it affects the results in the adjustment. But that's how we weight or we multiply the precision values of the vectors with the vector standard error factor. Adjustments, pretty straightforward. Least squares is using matrix math. It is iterating on a solution where as it iterates, as the coordinates come closer and closer, if we get to a solution, if we get to a situation where none of the coordinates change by less than this threshold, it considers the project converged. So maximum iterations of 10, convergence threshold of 2,000, 2,000ths of a foot, that is the standard. I always run with it. You will see though, you will typically never get over a few iterations. If you start getting into 7, 8 iterations, unless you've got a massive network, you've probably got something else going on that's going to show up that you have to address. Confidence level, we typically like to see 2 sigma to 95%. And some of this stuff gets over my head with like the different F distribution and normal distribution. That's what we try to use. And the relative error ellipses or alta report, the RPA or RPP, whatever you guys want to call it, this is becoming more and more important. It used to be, well, when you're doing alta reports, people were doing this where they look at the connections, the relative error ellipses of all the points of the boundary. It's becoming more and more common. I know we've got it in Michigan. A lot of people that I deal with across the country have it now in their state statute where they've got to report relative positional accuracy, relative positional precision, however you want to term it. Some people just call it ALTA. This is where we have a factor, like for an actual ALTA report, it's 700 plus 50 parts per million. That's what we've got set here. Some states have multiple, like they'll have a rural and they'll have an urban and they'll have some sort of an intermediate setting. I know Kentucky's got that, where they loosen up their standards in a rural situation versus in an urban situation. So we actually do want to look at our connections in this, and we'll actually, if we have this checked and we create a point list of the points that we want to check, it will generate the connection report for us, and that way we can actually certify to our state statute or to our ALTA certification that we've actually met the criteria. If I get into this, we'll actually see the list. These are all the points that I want to check, and it's going to check every single combination. So it's going to check 11 and 12. It's going to check 11 and 13. It's going to check 11 and 14. It's going to check 11 and 15. It's going to check 12 and 13, so on and so forth. So you can set this up. Typically, you want to select the boundary points. That's what we're certifying to. We're not certifying to, mapping points, topo points, that type of thing. So you can enter these by point number, which sometimes is a little bit inconvenient. But one other thing that's really nice is you can also set them by description. For example, iron rod found, if that's one of your codes, we can have it search for that description all the way through, and it's going to add that point into the list. So that's a little bit more intelligent way to do it than putting in a point list sometimes. But nonetheless, you can do it either way. If you want to look at a specific connection that you're really concerned about, you can type that in here, and that'll show up in the report as a specific connection. We'll get into that once we hit the adjust button on this. So that's all set up. So we got a couple of different things that we're adding to our report. We're going to have a compass type of closure, just to see what our error of closure is for a closed loop. and we're going to look at the RPA for our ALTA testing. I should show you also in the pre-processing where we have the closures, you can actually set up, if you wanted to, and this is where you can do multiple closures, you can actually have a GPS loop, but you would have to have a vector point to point. You can have a closed loop like what we've got, where we actually have a traditional closed traverse, or you can have a loop with an external exterior reference. That's where maybe you set up on point A and you have an azimuth line to point B. You run your traverse and you actually close out on that azimuth line. That's what that would be. So there's a few different types of closure here. There's also point to point. That's where you might have a, say you set a point pair with your RTK. You start on points 1 and 2, traverse across the site, and close out at points 3 and 4. That would be your point to point closure. So there's lots of different ways that we can close out a traverse. Lastly, we can get into the output options. Most of this is pretty self-explanatory. What's really nice about the output options is we can do a couple of different things. We can output to a coordinate file if we want to. Every time we adjust, it'll write to a coordinate file. And it's going to write in state plane coordinates. That's what this would be. We can write it to the current coordinate file, any coordinate file we want. I actually leave it off. And the reason for that is every time we do an adjustment in the background, right next to the SurvNet project, there will be a comma delimited text file. Well, it depends on your settings, but there will be an output file called with a .nez extension, and that will have your adjusted coordinates in it. And when I'm done with my adjustment, I use that file and I just import the points into Carlson and use them. But a lot of people want to have a ground coordinate system. And so we can actually set up our parameters and have it write the file automatically when we do the adjustment. So, and you can actually, you can pick your scale point, you can pick your scale value, you can calculate your scale value, however you want to do it to get it to come up with ground coordinates. I don't use that too often either. Some people like it. Just want to let you guys know that it's there. As far as our output for the NEZ file that I just noticed mentioned, every time you do the adjustment, there is a file. This is the format that's going to be the text point file output. And I actually like this one, point number, northing, easting, elevation description, comma delimited. That's the format I like to see. So we also have some global settings. We're going to use Carlson RW5 format. And I mentioned right off the bat that there was a standalone to get you into the legacy standalone feel of Carlson SurvNet, and that's where you would go to this, which requires a restart. We're going to stay in the docking dialog, though. I really prefer it. I didn't write it first, but after I got used to it, it's definitely the way to go in my opinion. There's also drawing settings. This is where you can set your layers, your symbols, the color of the lines. I've got this set up so that, my vector lines, if there's redundancy, come in red. If they're single vectors or side shots, they're orange. I've got my traverse line to come in as green, side shots as or blue, side shots as green, that type of thing. You can actually color code it, so you can actually look at a network graphically and know what the heck you've got. So in this case, GPS, we got a traverse line in blue. I got my side shots in the cyan color. I've got different symbols for my control or my traverse points, that type of thing. So you can customize that however you want. And what I do is in my drawing template, when I start up, I actually have all these layers set up so that when I work in SurvNet, they're there. And that way it looks the same every single time I do it. If you use the defaults, everything just comes in and is red. And so it's not as easy to look at on a glance. It helps me a lot in support because people send me their data and I can look at it graphically and I can tell, okay, here's their traverse, here's their instrument side shots, here's their GPS side shots, here's a GPS vector that's, sort of a closed loop or has a redundant measurement. So that's pretty helpful.